Hi everyone! In this video, we are going to be looking at systems of linear equations in two variables, and specifically, how do we go about solving these systems? So first we need to know what a system of linear equations is. So in the past, we've worked with a lot of linear equations, and they're usually in the form of y equals mx plus b, which we know as our slope-intercept form. But when we're working with our systems of linear equations, it's nicer for us to be able to have them in this form of ax plus by equals c. And so what a system of linear equations is when we have two or more linear equations working together, as we can see in this example here. So we have two equations. They are linear because the highest power we have is 1. So x and y are both raised to the first powers. And we have them in the form of ax plus by equals c. I will say that when you're given a system, they won't always be in that form. And as you'll see later when we talk about methods for solving these systems of equations, we will have to put them in that form. It's just nicer for us. So why is solving a system of linear equations important? So when we are looking at these linear equations in systems, they are a tool for modeling real-life situations. And so in learning the skills to solve these systems in two variables, it's going to help us later on, where in later videos, we're going to be looking at nonlinear systems and linear systems with 3 variables. So this will be very helpful in moving forward in the class. So, and like I said, we're working in 2 variables, so we're only going to be working with systems that have the variables x and y. A solution to a linear system, unlike when we're solving linear equations or our equations with rational exponents or our quadratic equations, we're not looking for one value. We're actually looking for 2, which makes up our ordered pair of x and y. And this ordered pair needs to make all the equations in our system true. So as we're talking about our different methods for solving, we are looking at 2 in particular, and those are going to be the substitution and addition methods. So let's first look at the substitution method. So we're going to follow these 5 steps. I'm going to go through them as I go through this next example. I would encourage you to read these steps though. But like I said, I will go through step 1, 2, 3, 4, and 5 as I work this next example. Now, one thing that I want to point out is that in step 1, it says that we are solving either of the equations for one variable in terms of the other. And so this helps us identify when the substitution method is going to be the most useful. And that is if we are already given an equation in our system that's already x equals and then all of our stuff, or y equals all of our stuff. This has already isolated the variable, and this is going to lend itself very nicely to the substitution method. Another thing that we might want to look for if we're looking to apply the substitution method is one of our variables easily solved for? And what I mean is it's not going to take 5 or more steps to solve for our variable, but it's just a simple 1 or 2, maybe 3 steps to get that by itself. And we'll see that in the example. Also, another thing that I want to emphasize is step 5, which is checking the proposed solution in both of the system's given equations. Checking is very important. So make sure that if we have one, no, or multiple solutions, we're checking our methods and plugging in those solutions that we do get to make sure it makes all of the equations true, not just one, but all of them. All right, so let's go ahead and look at our first example. So we're asked to solve by the substitution method, and we have a system of two equations, and they are x plus 3y equals 6, and 2x plus 8y equals negative 12. So first thing, like I said, is one of our equations easily solvable for one of our variables? And we can see that in equation 1, we can get x by itself in a few steps. So let's go ahead, and for step 1, we're going to pick equation 1 to solve for x. So we have x plus 3y equals 6. So if I'm solving for x, I want to get it by itself. So I need to somehow move this plus 3y. So I subtract it from both sides. And we're left with x equals 6 minus 3y. So step 1 is done. We have now solved for x in equation 1. So now what step 2 tells us to do is taking that equivalent expression of x, and we're going to substitute that in for x in our other equation. So in this case, in equation 2, wherever I see x, I'm going to plug in 6 minus 3y. So our equation is 2x plus 8y equals negative 12. So instead of x, I'm replacing that with our expression 6 minus 3y. So now we've successfully completed step 2. Step 3 tells us that now in our new equation from step 2, this is only containing y's and constants. So now we can solve for y. So let me rewrite this really quickly. So now, first thing I'm going to do is, in my parentheses, I'm multiplying by this 2, so I'm going to distribute it to both terms in those parentheses. So we get 2 times 6, which is 12, and 2 times negative 3y, which is negative 6y, plus 8y equals negative 12. I have like terms here, negative 6y and positive 8y, and we get positive 2y. And I still have this 12 in front, and then our negative 12. So now I'm trying to isolate y, so I want to get rid of this constant by subtracting 12 on both sides. And we get 2y equals negative 24. And we still don't have it completely isolated. We have this times 2, so we're going to need to divide by 2 on both sides. And when we do, we get y equals a negative 12. All right, so now we have an actual number value for y. So we can use this y equals negative 12 to find the value of x. There are multiple ways that we could find the value of x. One of them is we could plug our y equals negative 12 in equation 1 and solve for x. We could replace y in equation 2 with negative 12 and solve for x. Or when we solved for x in step 1 to get this expression x equals 6 minus 3y, we could plug in negative 12 for y there and solve for x. Any of these 3 ways is appropriate. I am going to go ahead and use one of our equations. So I'm going to go ahead and use equation 1. So x plus 3y equals 6. And so I'm plugging in negative 12 for y. So I do my multiplication. 3 times negative 12 is negative 36. And I want x by itself, and right now we're subtracting 36 from it, so I'm going to add 36 to both sides. and we get x equals 36 plus 6 is 42. So as of now, for our x value, we have 42, and for our y value, we have negative 12. And so our solution as an ordered pair would be 42, negative 12. But we need to check this solution, and we need to check it in both equations. So let's first look at equation 1. So our original equation is x plus 3y equals 6. And the first thing we're going to do is we're going to replace x with our 42 and replace y with negative 12. Now, remember, since we are checking, I'm only going to manipulate the left-hand side and see, do we get 6? So, order of operations, we're going to multiply first. So, 3 times negative 12 is a negative 36. And 42 minus 36 is 6, which is exactly what we had on the right-hand side. So that solution works for equation 1. What about equation 2? So our original equation was 2x plus 8y equals negative 12. So again, I'm going to replace x with 42 and y with negative 12. And again, I'm checking to make sure this works. So we're going to work with the left-hand side and see, do we in fact get negative 12? So we need to multiply first. So 2 times 42 is 84. 8 times negative 12 is a negative 96. 84 minus 96 is in fact a negative 12. So therefore, we do have the solution 42, negative 12. All right, let's go ahead and look at our second method, which is the addition method. Again, these are the general steps that you would use to work through solving linear systems by the addition method. One thing that I want to point out is in this case, for step 1, this is where we need to have both or all equations written in this form of ax plus by equals c. So if it isn't given to us in this form, we need to do that as step 1. And then when we are doing the addition method, we're trying to eliminate variables. So instead of having to solve one equation for a variable and then plug that into another, we are just trying to eliminate by adding the equations together. So we might have to multiply one or both equations by non-zero numbers so that when we do add the equations, the sum of the coefficients of our x's or coefficients of the y's is equal to 0. So we're canceling out one of the variables. And then also we have the very important step of checking our solution in all the original equations. This method is probably the most commonly used method for solving linear systems of two variables, and it can be used to solve any linear system, just like the substitution method. So first, let's go ahead and look at this example walking through those 6 steps. So we are asked to solve using the addition method this system 2x plus 5y equals negative 2 and 6x plus y equals 8. So step 1, like I had pointed out above, was to rewrite the equations in the form of ax plus by equals c. And if you look at our equations, they are already given to us that way. So step 1, we are good to move on. Step 2, we're going to eliminate x or y. And I am actually going to choose to eliminate x. You could do y, it does not matter. You should get the same answer in the end. So let's go ahead and we are going to multiply in equation 1. If I'm looking at my x coefficients, I want to end up by adding them together and getting 0 for my x sum. And so to do that, I'm going to multiply equation 1 by -3, because then I'll have a -6x, which will cancel out when added with this positive 6x. So let's go ahead and multiply by -3. And when we do, I'm doing that to each term in the equation. So we get -6x, then 5y times -3 is a -15y. And -2 times -3 is a +6. And then with our second equation, we had no change. So 6x plus y equals 8. In step 3, we're going to add the equations together. So I'm just going to go ahead and do that here, where we found them in step 2. So when I add them, -6x plus 6x, that cancels out. We get 0. And then we have -15y plus 1y, which is going to be a -14y. And then 6 plus 8, which is going to be +14. Now, in step 4, we are going to solve our equation that is resulting in step 3. So we're trying to solve -14y equals 14 for y. So in order to isolate y, the only thing that is happening to it is multiplied by -14. So we're going to divide by -14. And we have y equals -1. Now in step 5, we have a value for y. We need to find a value for x. So we can use either one of these equations, 2x plus 5y equals -2, or 6x plus y equals 8, to solve for x. And I'm going to go ahead and just use equation 1. So that was 2x plus 5y equals -2. I'm substituting in a -1 for y. And now I'm going to multiply. So 5 times -1 is -5. Trying to isolate x, so we want to undo this -5 by adding 5. And so we have 2x equals -2 plus 5 is +3. And then we need to divide by 2, and we get x equals 3/2. So now we have a value for x and a value for y. So our proposed solution is 3/2, -1. So now we need to check that this ordered pair does in fact satisfy both equations from our original system. So for equation 1, we had 2x plus 5y equals -2. Again, when I'm checking, I'm not going to work with the right-hand side. I'm only going to work with the side with my x's and y's and see, do we get -2? So replacing x with 3/2 and y with -1. Do my multiplication. So 2 times 3/2. Well, we're multiplying and dividing by a 2. So they cancel each other out and we're left with 3. 5 times -1 is -5. 3 minus 5 is in fact -2. So we do get a true statement. So now we just need to check it for equation 2. And that equation was 6x plus y equals 8. So now we're substituting in 3/2 for x and a -1 for y. Again, I'm not working with the right-hand side, only the left, to see, do we get 8 as an answer. So when I multiply 6 times 3/2, well, I could do 6 times 3, which is 18, divided by 2, and then -1. 18 divided by 2 is 9, minus 1. 9 minus 1 is 8. So we do, in fact, again, get a true statement. So our solution is the point 3/2, -1. The last thing that I want to talk about is our different possible solution combinations. So here I have created a table. And so we have only seen in those two examples when we get one solution for our system. But there are cases in which we can have no solution or infinitely many solutions. And so when we get exactly one solution, just like we've seen above, it means that we only have one value that corresponds to each variable. So we get one value for x and one value for y. And what that looks as a picture is that our two linear equations, which are lines, intersect at exactly one point. And that's the solution that we're finding. It's an intersection problem. When we get no solution, if we are going through the process of solving our system using either substitution or addition, and we eliminate all variables, and it results in a false statement. So if, for instance, we end up canceling out our x's and our y's, and we get something like 0 equals 4, which is wrong. That means that we have no solution. And graphically, that means that our two linear equations are parallel lines, so they never intersect. Therefore, they don't have a solution. If we have infinitely many solutions, that means that we went about solving our system using one of our methods, and we eliminated both variables, x and y, but we got a true statement. So if for some reason we ended up getting 0 equals 0, well, in this case, that means graphically that our two lines are actually the same line. So they're overlapping, and therefore any point on that line satisfies both equations. So these are different possible outcomes we could have when solving our system of two linear equations. Later on, like I said, we'll be looking at 3-variable systems as well as nonlinear and inequality systems. I wish you luck as you are solving your linear systems with 2 variables, and I hope you found this video helpful.